The modern superbike is more than just a motorcycle. It is a masterclass in high-performance engineering, designed to push the boundaries of physics on the track. To understand its capabilities, we must examine its anatomy. The structural chassis, the powerful combustion engine, and the electronic heart that governs its performance. The chassis defines agility, the engine provides raw propulsion, and the electronic sensors act as the nervous system, ensuring every ounce of power is harnessed with precision. The philosophy of the superbike is a delicate balance. It is not just about raw power, it is about the synthesis of speed and technological control. Superbike frames are evolving beyond aluminum. We are seeing the rise of graphene-reinforced carbon fiber. Standard carbon fiber provides high strength, but graphene-reinforced weaves integrate nanotechnology to improve structural integrity. This material excels at dampening high-frequency engine vibrations, significantly reducing rider fatigue during long sessions. At the heart of every superbike lies the four-stroke combustion cycle. It converts chemical energy into mechanical force with extreme precision. The intake stroke, the compression stroke, the power stroke. The exhaust stroke. In high-revving engines, this timing is critical. Even a millisecond of variance affects performance. This synchronization is what keeps the engine running at its peak. Superbike performance is defined by engine architecture. We compare the classic inline-four layout against the compact, torque-rich V4 design. Inline-four engines offer linear, predictable power delivery at high RPM, making them the standard for top-end speed. Conversely, V4 engines concentrate mass centrally and provide superior torque in the mid-range, allowing for aggressive acceleration out of corners. At the heart of the 2026 Ducati Panigale V4R lies the desmodromic valve system. Traditional engines use springs to close valves, but at 16,000 RPM, these springs struggle to keep up. This leads to valve float, where the spring cannot pull the valve back fast enough, causing it to bounce and lose timing. This limits the engine's upper rev range. The desmodromic system eliminates the spring entirely. Instead, it uses a secondary cam lobe to mechanically force the valve to close, ensuring perfect timing even at extreme RPM. By relying on geometry rather than tension, Ducati pushes the V4R engine into rev ranges unreachable by standard valve trains, maximizing power output. As we push engine power density to unprecedented levels, heat management becomes the primary limit on performance. High power creates extreme thermal loads. Cylinder heads can reach temperatures that threaten material integrity. To combat this, we use advanced nanofluid coolants. These provide 20% better thermal conductivity, allowing for much more efficient heat transfer away from the engine core. Modern superbikes rely on precision fuel delivery to maximize performance. At the center of this process is the fuel injector, which must deliver the exact amount of fuel at the precise microsecond. The engine control unit, or ECU, acts as the brain. It gathers real-time data from sensors monitoring throttle position, air density, and engine RPM to calculate the perfect fuel-to-air ratio. When triggered, the injector atomizes gasoline into a fine mist. This misting process ensures that the fuel vaporizes quickly, leading to a more complete and efficient combustion cycle. By refining this delivery based on millisecond-level sensor inputs, engineers can squeeze every drop of power out of the combustion cycle while remaining within strict efficiency standards. At high speeds, superbikes utilize ram air intake systems. Specialized ducts at the front of the fairing capture high-velocity air, directing it into the engine's airbox. As the bike accelerates, the intake ducts act like a funnel, converting the kinetic energy of the incoming air into static pressure. This forced induction effect increases the air density within the intake system. By forcing more oxygen into the combustion chamber, the engine can burn fuel more effectively at high RPMs. This results in a measurable boost in horsepower, effectively supercharging the engine at speed. Superbike engineering mirrors human physiology. The ride-by-wire system serves as the bike's nervous system, replacing traditional cables with high-speed digital signals. When you twist the throttle, sensors detect your input and send an electrical signal directly to the electronic control unit, or ECU. The ECU processes this command in milliseconds, calculating the optimal throttle opening based on gear, speed, and lean angle. Finally, the signal is sent to the electronic throttle body, adjusting air intake with surgical precision. This allows for instant performance and seamless integration with complex rider aids like traction control. At the heart of every modern superbike, located precisely at the bike's center of gravity, lies the Six-Axis Inertial Measurement Unit, or IMU. This sensor array tracks the bike's pitch, roll, and yaw orientation with extreme precision. The IMU processes physical data over 100 times every second, calculating exactly how the bike is moving through space. By comparing these values, the bike's computer instantly adjusts power delivery and braking, ensuring the motorcycle remains stable even during aggressive maneuvers. Superbikes now utilize active aerodynamics. These winglets dynamically adjust their angle of attack to manage airflow at varying speeds. By changing the winglet angle, the bike generates precise downforce. This prevents the front wheel from lifting during intense acceleration. Furthermore, during high-speed cornering, this increased downforce pins the front tire to the tarmac, drastically improving mechanical grip and allowing for faster apex speeds. Modern superbikes utilize cornering prediction AI. By integrating precise GPS mapping with real-time sensor data, the bike anticipates the geometry of an upcoming turn. As the motorcycle approaches the apex, the onboard computer maps the corner radius, allowing it to prepare vehicle systems before the rider even begins to lean. The system adjusts suspension damping and torque delivery with microsecond precision. This preemptive adjustment stabilizes the chassis, providing optimal grip for the specific arc of the corner. By minimizing electronic intervention latency, cornering prediction ensures that power delivery is perfectly matched to the motorcycle's lean angle. The Superbike transmission uses a sequential gearbox. Unlike a standard car, it relies on dog clutches for near-instant shifting. A quick shifter allows for clutchless gear changes. By cutting ignition for just milliseconds, it unloads the transmission, allowing the gear to slide into place under full throttle. This keeps the engine's momentum and power constant, which is critical for maximizing acceleration out of a corner. During aggressive downshifting, the engine's speed tries to match the transmission speed instantly, causing intense engine braking. This back torque can force the rear wheel to lock up, destabilizing the bike. A slipper clutch is a mechanical solution designed to limit this back torque. It uses a ramp and cam system inside the clutch basket. When the rear wheel pushes back against the engine, the ramp mechanism forces the clutch pressure plate to lift, momentarily disconnecting the drivetrain. This allows the rear wheel to spin freely without engine resistance. By preventing the rear wheel from locking, the slipper clutch maintains chassis stability, allowing the rider to maintain composure during deep corner entries. The chain drive serves as the final link between the transmission and the rear wheel. It efficiently translates the engine's torque into forward motion. Final drive gearing is a critical tuning lever. By changing the tooth count ratio between these two sprockets, riders can prioritize acceleration or top-end speed. Modern chains use internal lubricants sealed by X-rings. These reduce friction-induced power loss, ensuring more of the engine's hard-earned horsepower actually reaches the tarmac. Modern superbike suspension is no longer static. It is a dynamic interface between the machine and the track. At the heart of the fork, solenoid valves adjust damping rates in milliseconds. By processing input from the six-axis IMU, the system anticipates surface changes, ensuring a consistent contact patch for maximum grip. Modern superbikes now maintain a digital twin in the cloud. This system synchronizes real-time performance data with an owner's smartphone app. By transmitting telemetry from the onboard computer to the cloud, riders can analyze engine metrics, suspension loading, and wear patterns. This connectivity enables professional-level tuning and predictive maintenance, giving you insights that were previously reserved only for factory race teams. Whether you are on the track or in the garage, the digital twin ensures your machine is perfectly optimized. In modern superbike engineering, there is a clear industry consensus. We have reached a point of diminishing returns where raw horsepower is no longer the ultimate goal. The current sweet spot for a 1000cc machine is between 200 and 220 horsepower. Why stop here? Adding power beyond this threshold requires significantly larger engines or forced induction, both of which increase weight and chassis stress. Without a corresponding reduction in mass, higher output actually makes the motorcycle less rideable. Engineers are now shifting focus from pure output to usability and latency reduction. The challenge is no longer creating power, but how effectively the rider can apply that power through the electronics and chassis. Ultimately, a 220 horsepower bike that is stable and predictable is significantly faster on a circuit than a 250 horsepower bike that is physically exhausting to manage. This balance defines the current era of superbike development. Superbike engineering is embracing mild hybrid technology. By integrating a compact electric assist motor directly into the drivetrain, we solve the classic problem of low RPM torque gaps. While the internal combustion engine provides raw high-end power, the electric motor offers near-instant torque. This combination allows for a lighter engine overall, as it no longer needs to work as hard during low-speed acceleration. This predictive boost fills the performance valley, ensuring that the bike remains responsive, efficient, and incredibly fast, bridging the gap between mechanical heritage and future performance.